Till last class, we have seen how to design a CPU. So for designing of a CPU, what you have to do is, you have to finalize what are the instruction sets or what are the instructions that will be in the instruction set of the CPU. You have to finalize that what are the resources, that is how many registers, including memory address register, program counter, stack pointer, all these things have to be included within the CPU. And we have to decide the data path, a path which will take the data from one resource, one source to another destination within the CPU. And accordingly, you have to design the control circuit which will control the operation of the CPU, operation of different components of the CPU while execution of a particular instruction. And we have seen that the control circuit can be one of two types. We can have hardware control, where the control signals are generated by the combinational logic circuit along with some sequence counter. And in the other option, we can generate the control signals from a ROM, in which case we will call it as a software control or a micro-programmed control unit. So along with the data units, the control units, whether it is hardware control unit or the software control unit, taken together forms the central processing part of a computer. Okay. Now the type of CPU that we have discussed till last class, that is a class of a machine, a class of CPU, which is called a single instruction, single data, or SISD type of CPU. So SISD, or single instruction single data. That means the computers built with this kind of CPU is capable of executing only one instruction at a time, and that too only one data at a time. So this is a single instruction, single data type of computer. Now there are different types of computers which can be built as say single instruction multiple data, or SIMD, where we will have a number of processing elements. Okay. So when you say processing elements, it will consist of few number of registers and ALU, but the control unit will be same. Because it is single instruction multiple data, that means I will have a number of processing elements, but all the processing elements will execute the same instruction simultaneously, but on different data sets. I mean a type of architecture which is applicable for let us take for example say image processing kind of applications, where if I want to perform some operation, say for simplicity let us assume that we want to add two images. So you know that the images are nothing but a sort of matrix, where I can have an image size of say m by n. That means it is a matrix of size m by n, where every matrix element will represent some intensity value in digitized form. So it is the same operation which has to be performed on every matrix element. Okay. So for that kind of application, the kind of architecture which is suitable is SIMD, because it is the same instruction, same operation to be performed on different image elements. Okay. So there the kind of architecture which will be used is SIMD, or single instruction multiple data architecture. We can have other kind of architectures like MISD, that is multiple instruction single data, and this is mostly of theoretical importance, because getting an application where applying more than one operation on the same data simultaneously is hardly possible. But for completeness, we assume that there is some architecture called MISD, or multiple instruction single data. But another kind of architecture which is widely used is called MIMD, or multiple instruction multiple data type of computer. And you will see that this MIMD, this leads to a type of computing which is called distributed computing. So essentially, what is MIMD architecture is that we can have a number of independent computers. Each of the computer can execute different programs, okay, and the different programs will be executed on different data set. Maybe for coordination, if the different programs are part of the same task, then the computers need to interact while execution of on different data sets, okay, and that can be done via a network, via local area network, or some closely connected network. So different types of configurations are possible. We'll come to details on this later on, but for the time being, let us see, I mean, why people have gone for all these different kinds of architectures. It is simply to improve the performance of the computer system. Okay, that means we want to do more amount of job in less amount of time. Okay, so in order to do that, people have tried for these different kinds of computer architectures. Now let us see a simple concept by using which the performance of a computer can be increased. That is the concept of pipelining. Okay. Now what is this pipelining concept? Let me assume that I have been given a task, let us say a task, I call it a task T. Okay. Now this task has to be performed by a computer. If it is possible that this task T is divided into a number of subtasks, okay. Suppose I break this task T into a number of subtasks, say T1, T2, T3, and T4. Suppose I break the task T into these 4 subtasks, and when I execute, when I complete these 4 subtasks in this given order, the order will be decided by interdependency of the data. Okay. So when these 4 subtasks T1, T2, T3, and T4 are executed in this order, then this complete task T is executed. Okay. Now if I assume that I have some organization where I have different computing blocks. Okay. So I have a computing block, say S1, I have a computing block, say S2, I have a computing block, say S3, and I have another computing block, say S4, where this computing block S1 is capable of executing task T1, this block S2 is capable of computing task T2, S3 is capable of computing task T3, and S4 is capable of computing the task T4. Okay. So this is a kind of architecture that I have, right? And I also assume, for simplicity, that each of these subtasks T1, T2, T3, T4, each of them takes the same amount of time for computation. Okay? And I assume that time of computation for each of the subtasks is tau. Okay? So this is the computation time for each subtask. Right? Now find that if tau is the time for computation of each of these subtasks, then on a single processing machine, if I have to compute these tasks in this given order, then for completion of this task T, the time taken is 4 tau, because the task T has been divided into 4 subtasks. So the total time of execution for this task T is 4 tau. Okay? And if I have n number of tasks to be executed by the machine, then the completion time of n number of tasks is 4n tau. This is simple mathematics. Every subtask take time tau. I have 4 subtasks for every task. So every task will take 4 tau amount of time. For n number of tasks, it will be 4n tau amount of time. Okay. Now let us see another option, whether we can improve this total time required. Okay. So I have said that I have 4 processing blocks, S1 which is capable of computing T1, S2 capable of computing T2, S3 capable of computing T3, S4 capable of computing T4. And these tasks are to be executed in order 1, 2, 3, 4. Okay. So if I organize these processing blocks in this manner, okay, these are the latches. So whenever a task is to be executed, this is called a pipeline. The task is fed to the pipeline. Now for a task T, the first subtask that is to be executed is T1, and this S1 is capable of executing T1. Okay. So the S1 executes T1. Next, on the same task, the subtask that is to be executed is T2, and that is to be executed by S2. Okay. So after completion of subtask T1, for the same task, subtask T2 is executed by S2. Whereas this first block can be utilized for execution of T2 of the next task. T1 of the next task. Okay. So if we put this in the form of what is called a space-time diagram, the situation will be something like this. This is called a space-time diagram. This is the execution status of S1, S2, S3, and S4. Okay. During the first time interval tau, S1 is used for executing subtask T1 of the first task. So the task number I put it as subscript, okay, and the subtask number I put as superscript. So this is T11 indicates that this is the first subtask of the first task. So during the first time interval tau, S1 executes the first subtask of the first task. Then during the next time interval tau, because the first subtask is already complete, S2 can execute the second subtask of the first task. Simultaneously, S1 can be used to compute the first subtask of the second task. Okay. During next time interval, this one, the third subtask of the first task, can be executed by S3, the second subtask of the second task can be executed by S2 and first subtask of the third task can be executed by S1. So this way it can continue. So it can continue like this. Okay. Now here you find that once the pipeline is full, when I say the pipeline is full, when every processing block has got a job to be executed. Okay. So when the pipeline is full, then you find that after every time interval of tau, I get an output. Okay. Which, if I don't employ such a pipelining concept, then after every 4 tau I get output. Okay. So you find that if you have sufficient number of identical job to be executed, and if the jobs can be broken into a number of such pipeline stages, then by applying a pipeline concept like this, I can have tremendous gain in execution, or the system throughput will increase tremendously. Okay. So you can compute that if I have got 5, say k number of pipeline stages, k stages in the pipeline, okay, where every stage takes a time tau for execution, and if I have n number of jobs to be executed, okay, in that case, in a non-pipelined processor, the amount of time that will be taken is n k n times tau times k. This is the time taken for execution of n number of jobs on a non-pipelined architecture. Whereas, if I have a pipelined architecture, then you can easily find out that the time taken will be n plus k minus 1 times tau. Okay. So this gives tremendous gain if we go for a pipeline architecture instead of a non-pipelined architecture. Okay. Now, if all the pipeline stages takes an amount of time tau, in that case you can easily find out that use of these latches are not essential. Because whenever one stage completes its execution, the data from the previous stage is ready for passing to the next stage. So if every stage in the pipeline takes the same amount of time tau for execution, in that case we need not have these latches. But practically, having such a situation that breaking into pipeline stages where every stage will take the same amount of time is almost impossible. Okay. So in general, different pipeline stages will take different amount of time for execution, and in which case use of these latches are essential so that the data is not lost. Okay. Now in that case, we have to find out that at which rate we can pump in the tasks. Okay. So that will be decided by the stage which takes maximum amount of time. So I can decide tau in that case like this, that tau will be same as maximum of tau I, okay, where tau I is the time taken for execution for ith pipeline stage, where I will vary from 1 to k because we have got k number of stages, plus I have to incorporate an additional time because now I have put latches in between. Every latch will incorporate some delay. Okay? So if I say that latching delay is tau L, then tau is given by maximum of tau I, where tau I is the computation time of the ith pipeline stage, plus tau L, where tau L is the time latching delay. Okay? And from this, you find that the rate at which the task can be pumped through the pipeline is simply f equal to reciprocal of tau. Okay. So this is very simple calculation. Now let us come to a practical example where this pipelining can be very useful. Say for example, we want to add two floating point numbers. Okay? So I want to add two floating point numbers, say a, which is of the form a into 2 to the power p, where a is the fraction part, lowercase a is the fraction part, and p is the exponent part. And another number, floating point number b, which is given by b into 2 to the power q. So these are the two floating point numbers that we want to add. Now you know that whenever we want to add two floating point numbers, what is the best way or the most efficient way of doing it? You simply equalize the exponents. After equalizing the exponents, you add the fraction parts. Okay? So that fraction part along with the equalized exponent gives you the addition. And if necessary, you may have to normalize it. Right? So if I want to equalize the exponents, in that case, I have to compare the two exponents of the two numbers to find out what is the difference. Then the fraction of one of the numbers have to be either divided or multiplied by 2 or integer powers of 2 so that your number remains the same. Okay. So simply like this, if I have one number, say 0.5 coming to the decimal domain into say 10 cube, other number is say 0.3 into 10 to the power 5. What I can do is, I can equalize this. This number, I will equalize in such a way that my power will become 10 to the power 5. So if I put this as 10 to the power 5, I have to modify this fraction part. How you modify the fraction part? You simply give some right shift to this fraction part, and in this case, because I have increased the exponent by 2, that means this has to be given right shift by 2 digits. Okay? So this fraction part now becomes 0.005 times 10 to the power 5. Number remains the same. Only some adjustment among exponent and the fraction part. And here it is 0.3 into 10 to the power 5 as before. Okay? So whenever I want to adjust the exponent and fraction part, I have to know that what is the difference between the exponents. Okay? Increase the lower exponent by the required amount and give right shift to the fraction part by the required amount. After this is done, your addition is very simple. This becomes 0.305 times 10 to the power 5. Right? So the result will consist of two components. One is the fraction, which is 0.305, and other is the exponent, that is 5. In some cases, it may be necessary that after performing this addition or subtraction, whatever it is, if you find that there are some leading zeros in the fraction part, normally what we want is the leading zeros are to be eliminated. That means I have to count how many leading zeros after decimal point you have in the fraction part, then give left shift to the fraction by so many digits, and because you are giving left shift, that means fraction you are multiplying by 10 raised to the power the number by which you have given the left shift. You have given the left shift. So many times I have to reduce the exponent part. Okay. So all these operations are to be done when we want to perform the addition or subtraction of two floating point numbers. Now let us see that if I want to perform similar type of task through a pipeline processor, what are the pipeline stages that we need? Okay. So the first component in the pipeline stage will obviously be two latches, which will latch the fraction and the exponent. So I have two latches. One latch will take the exponent part and fraction part of the first number. So exponent part P and fraction part A, because we have said that we have to add number A equal to A into 2 to the power P. This is the first number. And the second number that we want to add is number B, which is B into 2 to the power Q. Okay. So this will also take exponent Q and fraction P as input. Then the first operation that we have to do is compare these two exponents P and Q, and this will be required for normalization purpose. So I must have an element which is able to compare the exponents. So this is exponent comparator. Okay. Exponent comparator will take the exponent P and exponent Q, right, and it gives some output, right. And once I find out that which of the exponent is greater or which of the exponent is lower, I have to select one of the fractions, one out of this A and B, for normalization. Okay. So on this side, I have to have an fraction selector. Okay. Fraction selector will take these fraction inputs B and A. It will get a signal from the exponent comparator to tell you that which of the fractions is to be selected. Okay. Now once you select a fraction, then I have to give a required number of right shift to the selected fraction. Okay. So I have to have a right shifter. Isn't it? Simply by this example, I have taken this fraction 0.5 and given right shift to this by 2 digits. Okay. So I have to select one of the fractions, give the required number of right shift to that selected fraction. So this will get an input from the fraction selector, and at the same time I have to know that how many digits, or in this case how many bits of right shift I have to give, and that depends upon what is the difference between P and Q. Okay. So from this same exponent comparator, I get a signal which will indicate that how many bits of right shift is needed, and this is equal to given by subtraction difference of P and Q. Okay. So many bits of right shift has to be given to the selected fraction. Okay. And after that, what I need is, so following this, I can put another latch. So you see that output of this right shifter is the normalized fraction. Okay. I have to add this normalized fraction with the other fraction which is not normalized. So I have to have other fraction coming to this latch. So this gives you the other fraction. Okay, and here from the exponent comparator I get the maximum exponent. Okay. Now after performing this, I need one adder element. That is the fraction adder, which will add the original fraction with the normalized fraction, okay, to give you the resultant fraction, right. So this resultant fraction I can latch into another one, and the exponent that is selected, you find that the number of latches that you need in both these paths have to be same. Otherwise, there will be time delay and may lead to data loss. So the number of latches that I have in this path have to be same as the number of latches or the stages of latches that I need in this path. Okay. So this gives you the resultant fraction. After resultant fraction, typically what we need is leading zero counter for renormalization of the resultant fraction. So here I have to have a leading zero counter okay. Then the same one, depending upon the number of leading zeros you have, I have to give left shift to the resultant fraction, and number of bits by which the data has to be left shifted, that depends upon how many leading zeros you have. So this is a block which gives left shift. Okay. And by whatever number of bits you have given left shift to this, this exponent has to be incremented by the same number, isn't it? Because if I give some number of left shift to this, that means I am multiplying by the number. If I give 1 bit left shift, that means I am multiplying the fraction by a factor 2. 2 left shift means multiplying by a fraction 4, by a factor 4. Okay. So by whichever amount, by whichever number you give left shift, the same number has to be deducted from the exponent, because one multiplication has already been done here. So to keep the number same, the same number has to be deducted from the exponent. Okay. So what we have to do is we must have an exponent subtractor, or which can also be done by adder, because you know that subtraction can also be performed by adder. So I'll put it as exponent subtractor. Okay. And this exponent subtractor has to get the output from this leading zero counter. The exponent will be subtracted from this selected exponent, and then finally what you get is the result. So I'll put one more latch here. So here I get the final result, and the final result in the form, suppose this is the exponent and this is your fraction part d. So your final result will be simply d into 2 to the power s. Okay. So this can be a total pipeline architecture for addition of two floating point numbers. Now what is the advantage that you get by using such a pipeline architecture? If I have an application where I simply have to add two numbers. Just two numbers I have to add to get a result. Does this pipeline architecture give any advantage? Possibly no. The pipeline architecture gives you an advantage when you have to do identical operations on a large set of data. Okay. So for example, if I have two linear arrays of floating point numbers, arrays A and B, and these two arrays are to be added to generate an array C, again of floating point numbers. The array may be of size 100 or 500 or 1000. That means I can consider that each of the array is a vector where every component of the vector is a floating point number. Okay? So two such vectors I have to add to generate a third vector. Okay. In such kind of application, this type of array architecture is very useful. Okay. So first you feed in the first component of the vector. After computation of the first stage in the pipeline, the first component comes to the next stage, when the first stage can be used to compute the first pipeline function of the second components. Okay. So this way if you proceed, you find that this pipeline architecture gives tremendous advantage over non-pipeline architecture, and the amount of gain that you can get, we have already said, is this much. For a non-pipeline architecture, you have n times tau times k. For a pipeline architecture, this multiplication is reduced to an addition, that is n plus k minus 1 times tau. Okay? And this gives tremendous advantage when you have identical operations to be performed on a large volume of data. And that is what leads to the concept of vector computer or vector processor. Okay. So in case of vector processor, the type of application that you need, suppose I want to add two arrays.
So in that, how we can assume that all the computation blocks are performing at the same speed? Because we are saying that
no, they are not. They are not. That is why these latches are put in between. So what we have to decide is at what frequency or at what rate the pipeline should work. Okay.
So one more thing, that different block, that is the comparator, redshift, output, this all has to work at the same speed, because we are saying that the number of latches should be same.
No.
The number of latches we have used.
Number of latches in this, see here I have two distinct paths. Okay. I can simply demarcate between two paths. This side deals with the exponent, this side deals with the fraction. Number of stages I have to have on the exponent side has to be same as number of stages I have to have on the fraction side. Otherwise, the amount of delay that you incorporate on this side will be different from the amount of delay that you incorporate on this side. And because of this delay mismatch, it is possible that you get only the fraction, you don't get the exponent. Or you get only the exponent, but you don't get the fraction. Okay. So to avoid that, you have to ensure that whatever delay you encounter here, the same delay should be encountered here. Okay. There can be delay mismatch between different stages. So here, this is one stage of pipeline. This is another stage of pipeline. Okay. Maybe this can further be subdivided. I mean, the number of pipeline stages that you have, more the number of pipeline stages, more advantage you get. Okay. Your speed gain is more if you have more number of stages in the pipeline. So this can be broken into further pipeline stages. That is also possible. Different pipeline stages may take different amount of time. So this will be more advantageous if we can come close to the ideal. Now what is close to the ideal? That every pipeline stage will take some amount of time for computation. If I can guarantee that, in that case, some of these latches I can avoid. Of course, on this side I cannot avoid, because here there is no computation, simply passing the data from one to another, from one latch to another. But assuming that in every stage I have some computation, and every stage takes same amount of time for computation, in that case, the latches are not necessary. But If the time taken for different stages of the pipeline is different, in that case it is necessary that I have to put a latch, otherwise the data will be lost. Okay. And if you want to put the latch, in that case you have to decide that at which frequency the pipeline has to operate. And this is the equation for that. Okay. So you find that the pipeline frequency, the rate at which the pipeline has to operate, depends upon the stage which takes maximum amount of time. And that is what is called pipeline bottleneck. Pipeline bottleneck. Because it is the block which decides maximum at which rate the data can flow. It is simply the concept of a bottle. At which rate you can take out the fluid from a bottle, that depends upon what is the width of the neck of the bottle. Okay. So that is why the concept came, the naming came, that it's a pipeline bottleneck. Okay.
So structurally, all the latches have to be identical.
Structurally, all the latch, what do you mean by identical?
Identical as in the same amount of data is going through the pipeline. So will the delays have to be the same?
Delays have to be the same. Yeah.
So, but
Delays have to be the same. But see, ideally what we assume is all these are synchronous circuits, all the latches. Okay. They operate only either at the rising edge or at the falling edge. They are always latched. Okay. And there are various such examples in which we can have such pipeline computation. Okay. Now, this is a type of pipelining which is called execution pipelining. Okay. Now, let us see that how the simple pipelining concept can be extended to the CPU design. We have said that in case of any CPU, execution of any instruction consists of a number of cycles. The first cycle is an instruction fetch cycle. I call it IF. The second operation that is to be performed on this instruction which has been fetched is instruction decode. So I call it instruction decode or IT. After the instruction is decoded, then only the instruction can be executed. So I call it the instruction execution cycle. Now find that when instruction is fetched, the CPU makes use of the address bus, external data bus, memory, all these things, the control bus. When the instruction is decoded, in that case, those things are not needed. You don't need the address bus, you don't need the data bus, you don't need to access the memory. Okay. Similarly, when instruction is executed, the instruction decoder is not needed. Address bus, data bus, memory, control bus, all those things are needed optionally depending upon what is the instruction that is going to be executed. If it is a memory read or memory write instruction, in that case, all those external buses, address bus, data bus, and memory, they will be used. If it is something within the CPU, say for example transferring a data from one register to another register, in that case none of these external buses are needed. Okay. So it was thought that why don't you make use of these buses to prefetch some instructions when they are not really needed for execution of the already fetched instruction. That means essentially what we want to have is overlapping of these different stages of different instructions in time, which will lead to a pipelining concept. Okay. So that we'll see in the next class.